Welcome everyone, and welcome to RISSB's 34th Masterclass webinar. It's the last one for the year, and I can't believe it. Where has the year gone? And when we started these webinars in April of last year, we never thought that we'd be running 34 of them, or we would get the strong support and attendance that we have. Since we started them, we've had well over 7,000 people attend on the day or listen afterwards. And in fact, our most popular webinar has had over 680 people view it or listen to it. As I said, we started in April 8th with Howard Collins. And Howard talked about his illustrious 40-year career in the rail industry and about rail now and the future. And we're ending with Dixon and Matt Smith talking on complexity associated with remote software deployment. And in between, so we've been on a real journey. We've covered a range of topics from leadership, technology, digital engineering, because I have trouble saying digitization, it doesn't roll off the tongue, and human factors. But one common theme throughout all our webinars have been the importance of people and culture. And this is what's important to RISSB too. So we really want to thank you for your attendance and your strong support for the webinars. We hope you found them informative, but also enjoyable. We will start up again in February of next year, and we've already have a gangbuster lineup, and more details will be coming through to you on that. And we hope you continue your attendance. And before I turn it over to Chris, Matt, and David, on behalf of RISSB, we'd really like to wish everybody a very happy and merry holiday season and a happy, healthy, and safe new year. Thank you everyone so much. It's been an absolute pleasure. And with this, I kind of feel bad. It's our last one. I'm passing the baton to Chris, Matt, and David. So over to you guys. I am really looking forward to your subject. Thanks, everyone. Y'all take care now.
Thank you very much, Deb, and thank you very much for the message on Christmas and what's coming up. Let's hope that we have a great 2021. It's my absolute pleasure today to introduce Matt and David from Calibre Global. They're going to talk about a very topical area within the rail operations, which is the deployment of remote software in an operational context. With different systems coming online and us moving to more digital style locomotives, rolling stock, train control systems, etc., there is an increasing requirement to update these systems whilst the whole system is still operational. And now we're not only talking about within a city or within a state, we're talking about this nationally and potentially even internationally. Matt and David have worked a fair bit on this subject, so I'm really looking forward to hear what they have to say. Matt is a successful technology innovation leader with a commercial acumen, global program management experience, and skills in developing and inspiring high-performance technical teams. I worked with Matt at Calibre on the Auto Haul project. Matt was a senior project engineer there, and I look forward to hearing from Matt again. It's always great to be back working with him. David is a lead systems engineer at Calibre, who is providing both technical and delivery management to optimise the outcomes for the clients within this project scope, timeline and budget. During 14 years working with consulting engineering firms in Australia, David has gained experience in many areas, from project management through to rail safety system development and delivery. Overall, David has a mix of technical and management capabilities that are suited to today's heavy technical requirements. And as you can imagine, this is a major one. So without any further ado, I will now hand over to David and Matt. If you have any questions, please send them through using the chat function, and we'll attempt to address them as the presentation continues. Thank you very much. All yours, David and Matt.
Thanks, Chris. Great to work with you again too. At Calibre, we take our roles very seriously, and as an architect, I'm going to cover the problems, and as the engineer, David's going to cover the solutions. So when you get to the questions, David will answer them all. So what are we going to cover? We're going to cover the needs. What's actually driving this desire for remote software deployment in rail systems? And we're going to look at the goals, the outcomes. What do rail operations teams get out of using remote software deployment in their systems? And what are some of the key considerations from that we've learned from our work in this space? Now, we must give credit first to some of our colleagues who have actually done a lot of the heavy lifting in this space that we've benefited from. One in particular, Mr. Tom Naum, is really the father of a lot of the knowledge that we've gained in this space. So, quick coverage of what Calibre is, who's Calibre. The boss made me do it. We're a diversified professional services firm covering a lot of different spaces. That's probably enough on that slide. And then, of course, across the different spaces, we also have one focus that we're interested in today, and that's on the right there, the rail infrastructure and technology space. And specifically, on the next slide, there's all of Calibre's rail clients. So we've touched quite a few rail clients around Australia and other parts of the world, obviously in different levels of detail with those different clients. Not everybody has automated train running on ETCS system, but across the variety there, we hope we've added some value to numerous clients' rail operations. So what software are we talking about here? Today, we're really going to focus on locomotive software, and that's partly due to the time constraints of the format, but also because locomotives really present a unique distributed software management problem, and it's in an intensely safety-focused portion of the rail network. Wayside systems, of course, have their own issues, but they tend to have fewer interdependencies when it comes to creating integrated solutions and management of the configuration of those solutions. Back office systems also face similar problems to locomotives, and they are often tightly coupled with locomotive systems, but you don't have to travel far to update all the systems in the back office. So what sorts of locomotive systems are we actually talking about here? To start with, there are the general onboard systems, the locomotive control systems from the locomotive vendor, automatic train protection systems, including in-cab signaling and driver interfaces, data loggers and judicial recording units, and also things like location systems, GNSS, odometric dead reckoning systems. These all have software today, and that all needs to be managed coherently. Of course, modern locomotives, nothing without its communication systems. The radios, modems, routers, switches, all have software in them that needs to be managed. And this is the basis for the more sophisticated systems like ETCS, CBTC, and ATMS. And it's how all the systems on the locomotive that have connections to their back office manage to provide the functionality across the board. There are numerous components in locomotives that integrate with offboard systems. Of course, in mining, we see loadout controllers at the mines and dumpers at the ports that have interfaces to the locomotives. In freight systems, we see container movement environments and other freight management systems. And of course, electronic train graphs are common across the board. Automation, of course, is becoming more and more common, a very common goal amongst operators due to its efficiency gains. And that means that there are things like driving strategy systems, which start with driver advice systems before we get into full automation, but also video surveillance systems, collision detection systems, and overall controllers that drive automated train operations. All of these systems are driven by software, and they all have to have a coordinated delivery of that software. If you thought that keeping the software versions of these systems updated and consistent looked difficult, don't forget they also all depend on configuration data. Things like track databases, speed restrictions that are updated continually, and all sorts of other configuration items. So that's the software we're talking about today. What's actually driving the change that's pushing us towards remote software deployment? After all, software has been on board locomotives for decades. Traditionally, at first I wanted to call this slide historical view, but realizing, of course, that many systems today still work this way. So it's really the current view. And these current onboard systems tend to come from single vendors, and they tend not to be connected. There are exceptions, of course, but in general, they're not connected to the network or even to other onboard systems, particularly if there's no requirements driving any integration. Why make a simple, why make a more complex system than you really need? Systems are typically updated by the various suppliers and vendors directly in vendor-specific ways. Any interaction between the systems is not only controlled, but it's very minimal. So because of loose integration, there used to be, and there are in these current systems, very few dependencies when updates happen. In other words, you can update one system without impacting others. Typically, you could wait weeks or months to deploy a software update. Indeed, if planning goes well, we can often synchronize software updates with equipment mechanical maintenance cycles. So when locomotives touch the workshop, that's when the software gets updated. And software updates are traditionally done manually. So staff board the locomotive using a USB key, a laptop, or some other equipment to deploy a software update onto the onboard systems. And they can also perform the safety validation checks that are necessary at that point. So what's actually changing that's making this drive? These things here are not necessarily in any order. They're also quite interdependent upon each other. Naturally, the first one is big and current cybersecurity vulnerabilities. You knew we couldn't go far before this had to come up. Driving rapid change here. Risks can crop up literally overnight. So many onboard systems depend on their network connection to function, but that's also what makes them vulnerable. But don't forget that even systems that don't use the network are vulnerable because they connect to systems on board the locomotives that do connect to the network. So there's chain effects there. Some of the change drivers also originate in regulatory frameworks. A greater degree of regulation and the associated technological drivers for the regulator also drive changes like this in the industry. This is a bit of a circular relationship, but it is hard for a traditional operator to continue operating in the way that they always have. Also, significant advancements in technology. Much new technology has software embedded in it, as I covered in the previous slide. Many of the vendors rely upon technology to provide the value-added services and features that are important to operators. Improved communication mechanisms allow for greater distributed integration. Improved locomotive location systems, GNSS, enable enhanced location of trains. So that's the technology driver. Increasing complexity also has safety implications. Of course, this applies to many parts of the system, including wayside and on board. New safety systems such as ETCS, CBTC, ATMS are a major driver of these needs, as are new safety standards such as Senelec and the compliance with those standards. Underpinning railway operations alongside safety is expectations of operational efficiencies. All rail operator assets. This is really the biggest driver of these changes. And improvements in maintenance, tracking and preventative maintenance, optimization of vehicle performance to reduce wear and tear, to reduce fuel consumption. Optimizing vehicle performance by using driving advice systems. Planning and vehicle movement. It's all part of the drivers here. All that leads eventually to vehicle automation as the most efficient way to extract value from rail assets. So those are the drivers. What is it that's changing so much that we need to look to remote software deployment to keep up? It's really the variety of the new systems that are appearing on board and the mechanisms by which they're delivered and the demands for system availability collectively. These together necessitate a structured response to the software environment on board the locos. Some key factors: railways are facing an increasingly more complex software environment. So the systems themselves are more complex and they typically have many elements, both on board and off board. The elements need to operate in an integrated fashion. Failure in this means the trains stop. Many of the systems are data-driven. As I mentioned, the configuration management. And this provides another level of complexity. Something as simple as the configuration of a router can be critical to the overall operation of the system. In addition to individual systems becoming complex, many systems are also becoming highly dependent on each other. While we expect systems to rely on input from sensors on board, more systems now rely on other systems as well. Often the interconnected systems are supplied by different vendors, and this fact alone really increases the complexity of the problem. No longer can one system be updated independently, but because they communicate and are dependent on and connect to each other, updating one can introduce changes that mean the other systems stop working. Having so many systems in itself implies more software updates. So with interfaces between systems and probably configuration data dependencies as well, changes in one system can impact many others, resulting in a cascade of changes, which must be managed in a synchronized and coherent way. So we're coming up to question time in a bit. So just wanted you to prepare your questions for David to answer. And I'll just finish off this slide. The rail business and operators have increasingly high expectations that systems management activities such as software updates will have minimal impact on business operations. Many rail operators are mindful of asset costs while wanting to maximize revenue. This drives improvements and optimizations in utilization of available assets. Of course, the pressure isn't the same across all categories of rail operators, but for some, having assets unavailable for extended periods directly equates to lost revenue. So improving utilization also has indirect savings in that maintenance costs are amortized over more operating hours. Target of automation ends up being 24/7 operation with as little time possible and in the unutilized state. So any stoppage has a negative impact on the goals of the business. Of course, the standard approach for software updates is to wait until all the locators are out of service at night, when they can be boarded and have the new software deployed and verified. But this is becoming less tenable. While many passenger systems still have a shrinking maintenance period, most freight and mining operations are 24/7. So there is no defined maintenance window. Certainly not one in which the whole fleet can be updated at once, which can be the case with onboard changes that are tightly coupled with simultaneous back office changes. Generally, freight and mining networks are distributed across large geographic areas as well, presenting even more issues, particularly where you consider the updates are likely interdependent, so not allowing for any delay in deployment. Signaling data for an ETCS or CBTC system is an example of that. Finally, and you knew it was coming back, cybersecurity scene has changed dramatically and changes continually dramatically. They're unquestionably increasing, these changes, especially as railways are a core part of a country's strategic infrastructure, and disruption can have a major impact. So not only is this important at the state actor level, but can create major street cred for a hacker kid in a basement somewhere. At the same time, rail operators have increasing appreciation, or have developed increasing appreciation for the risks and ramifications of cybersecurity failures on the railway. And even as we manage to get our heads around the other challenges, the dynamic nature of cybersecurity is not going to diminish. So Chris, how are we doing with questions?
We've already got a couple through, so that's great. Thanks, Matt. And I'm sure we'll get a lot more once David goes into the technical side of things. But we'll start off with the first one. So this is one that's just recently come through. For safety critical systems, how effective can automatic version and configuration detection and reporting be as a risk control? I've been told it's essential for specially trained humans to check configurations on safety critical systems on onboard rolling stock.
It's an interesting question, that one, and it's always comes up in systems and safety assurance. And I always go back to the very first point when you look at your, for example, a Senelec analysis about what the reliability is of particular elements, i.e. engineering control versus a human. And I think the standard Senelec failure rate on a human is about 1 in 1,000. So even highly trained humans, this is my personal opinion, even highly trained humans won't be able to match the efficacy of a well-designed system. Now, systems do fail, and you cannot have the system that's loading the software validate the software that they've loaded, because failure may necessarily propagate to the point where it also feeds back incorrect data. So what you do is you effectively emulate what a person would do if you want to automate that process. And you must have a complete independent implementation doing the validation. Much like when you have your 2 out of 2 or 2 out of 3 on your ATP, in theory, this doesn't occur a lot, but in theory, you should have independent developers providing the two halves, so it mitigates common failure modes. And you're using exactly the same principle in this case, but with the software delivery side, where you have multiple software elements performing the same validation. Any discrepancy causes the system to halt, and therefore the safest mode.
Great, thank you very much, David. Another question that I've got here for you. Communications systems, often third party, are so critical to rolling out software in this sort of world. Do you see an increasing need for systems such as 5G to be rolled out nationally to allow this sort of work to occur?
We'll cover a little bit more on comms a little bit later, probably elaborate a bit further, but yes, to a degree. 4G, for example, has good coverage, and you can never assume a communications network is reliable. So it doesn't matter how good it becomes or how pervasive, you end up with a situation where you have to assume the comms is going to fail you right when you need it. And that's one of the premises of software delivery systems is you don't do that. Now, you're like using your phone. It might only fail, once every 6 months, but that's enough to take a complete deployment out and stop your entire network for days, however long the system goes out. And also, a lot of the comms networks aren't redundant. So Telstra towers, for example, are not necessarily overlapping. So you get to a situation where you have to design your software around the fact that it is unreliable, but having 5G does help in that it speeds the delivery. In addition to that, and we'll touch on this later as well, is some of the systems on board, such as ETCS type ATPs, they require a connection to their centralized interlocking. If you go that far down the ETCS path, where they require their authorities to be delivered. So you get into a situation where you do rely upon comms, but from a delivery perspective, you don't want to get into a situation where you've been unable to deliver a portion of your software delivery, so you deliver early, essentially.
I think one of the important things in that space is really that you don't think that you're going to do an update as soon as you push the button. There's a caching exercise there. You take some time to ensure that you get the update to the locomotives before you actually deploy it. So you can cache it on board, and you can deal with some outage in the comms as you're trying to do that. It takes some time, obviously, but you can be then quite confident that everything's available on the locomotive before the actual go happens.
Great, thank you very much. All right, well, let's keep going. So I hand back over to David, and let's hear about some of the solutions.
Okay, so we've heard about what we've got. What does this mean? So it means we've got to change what we currently do. And to be very simplistic, I suppose we've got a few key areas we've categorized it in. So we've got to change the systems. We've got to change maintenance, which is maintenance in both, practice as well as procedures. And we've got to change our governance as well. We had a discussion a bit earlier about ONSA, and that's part of what's got to come into play. Not just governance from the rail operator, but also governance from the regulators as well. So it goes across the board. I'll go through that a little bit on the next few slides. So what I'll do is I'll go through a few slides and then ask for more questions. So if you have any questions, ping them through as I run, and we'll get to answer them in another few slides, but I'll do that. Now, getting back to the software implementation. So interestingly enough, this remote delivery we're talking about, and a lot of these aspects, they're not new to software engineering. Industries have been doing this for years. They've been forced to do it. If I take an example, your ATM network where you get your cash, if that had outages because of delivery or different versions where you couldn't have different versions, it's going to end up with a situation where people don't have their money, and people are usually fairly attached to their cash. So that would present a problem. So those sort of industries have been dealing with this for quite a long time. So there are lessons to be learned from this. Now, we know these principles don't apply directly. It's not in this exactly the same environment. They are on fixed networks generally, but and things like that. But generally, the principles that they've brought to bear are fairly good in general. So we need to apply that. So in a lot of cases for rail, where we have specific engineers that have been working in the rail industry a lot, they're typical of most engineers. They're very familiar with what they've been doing and not necessarily what has been done elsewhere. So that's not always the case, but it is typically the case. So we need to consider that when we're doing these sort of implementations. And what's our goal? So our goal is to deploy a consistent set of software, and that's referencing versions to a variety of subsystems reliably. We don't want to have a delivery that's corrupt, for example. We need to do it securely, so a level of sort of non-repudiation where we get to a situation where you can verify at the destination that the data hasn't been tampered with. This is coming back a little bit to that cybersecurity thing. And I suppose we also need to look at how we deploy the software onto the environment. So we now have many different subsystems interacting. So where they interact, you need a common language, to put it simply. For example, track topology. So if you have track topology, and you have the different systems communicating about a particular location on the track, they both need to talk the same language, in that they both need to know where they are. So that's part of this deployment. So it's, again, as Matt said, not just software, but also data as well, because the data is integrally tied to the software as everything else. So challenges. So overall, I suppose just in a little bit more detail, we'll go in more detail in a bit. Systems. So they're the various systems that are managed. So we'll have ATP systems, we'll have braking systems, we'll have loco systems management systems, we'll have driving strategies, we'll have numerous systems, communication systems, you name it. There's lots of them on board a loco. Dependency links. Now this one, I probably shouldn't have used the word dependency links because that's a bit too simplistic. So this is the dependencies between things that are being upgraded. So I'll go into that a bit later. Accessibility, and we sort of touched on that in one of the questions. So locomotives need to be accessible, but we also need to consider the fact that they may not be accessible. So if we're looking at, for example, ARTC running trains across the Nullarbor, there's quite likely to be areas where the system is not accessible at a point in time. So therefore, you're not going to get to it. Workshops is another classic example. You've got a loco in for maintenance, the system shut down. There's no way it's going to upgrade while it's shut down. So there's aspects that we need to deal with in that state. And then we got the last one, which is state. And by that, I mean what state the loco is running in. So is it mainline running? Is it, if you're, for example, a mining company or a freight company, loading, unloading, banking locomotives, shunting, maintenance? So all these different states the locomotive's in, you've got to consider these as you want to run your upgrade software. So you would consider every one of those aspects, basically. A lot of these things can be procedurally resolved, but typically if we're implementing, would prefer an engineering solution where possible. So as we know, in your hierarchies of control, you get to a situation where engineering solution is generally considered more reliable than a human solution, which is procedural. So where we can, we would do an engineering solution, but that doesn't apply in all cases. So when we build a solution to address the challenges, we basically need to build in the system in multiple layers. So we build a core system, we build components that sit around that. We then build processes that sit around that. And underlying the whole lot is, I suppose, the systems that are currently in existence as well, which is a complication in its own right, one of the most complex complications. So challenges, this is the systems components. So there's probably two key challenges. So there's lots of challenges in this area. You can't underestimate how many challenges there are, but there's two of them that have consistently caused us problems in this type of implementation. So one is, well, first one is interfacing and integration with vendors. So we have specific vendors. They like supplying their systems. They like being insular, protected, not having to integrate to other people or be reliant upon other people. That's another aspect. They go to great lengths to avoid having not only any interaction, but also to have somebody else interact on their behalf. And this is what software is doing in this case. You're trying to deliver an element that they require, but you're not using their traditional mechanisms. So in this particular case, they come up with all sorts of excuses. You have political excuses, you have commercial excuses, you have intellectual property excuses. But overall, typically when you communicate to them and you explain what you're trying to do and the fact you're trying to integrate numerous components, they typically come around. So that's not necessarily required, but it's highly recommended. So the main reasons being, if you've got an interface that's defined or at least documented from a vendor, it becomes significantly easier to implement an interface to that subsystem. So we can build an interface relatively easy, even if it's something as simple as a file drop in a directory for a legacy system, and then trigger a script which then updates the system. We then need means to validate as well the system's been correctly updated. So that's the most simplistic and brutal case. A direct interface, a software-based interface, is by far the much better way to do it because you have real-time access. But very few systems supply that at the moment. So you can do it, but it's much rarer. What else is there? I suppose there's other ways to get around things. So if a vendor doesn't want to provide you with information, we've had to do this in the past where you look at how they do things and you replicate it. There's other mechanisms you can use to upgrade applications, such as imaging. Again, it all boils down to the specific implementation of that particular subsystem. And you generally need quite skilled software engineers when you don't have any cooperation, but you can work around it. And for example, some of the systems we've done, in the end, after 6 months or a year, they see the benefit of what's occurring, and typically most of the vendors do come around and start assisting. It does help if you pay them some money to do the work on the interface, obviously, and that's typically where it gets to, but in the end, we do get somewhere. Dependency links. So I mentioned this, calling it dependency links is probably not a good idea. It's more of a reflection of what is my upgrade scenario. So not only does it define the links between the different subsystems, so as an example, in a subsystem, when you upgrade the loco control system, for example, you may change the interface that another system uses. When you do that, it obviously becomes incompatible. There's certain scenarios where you can build in backward compatibility and roll your upgrades. That's okay, but then you still want to automate it. You don't want an upgrade taking 3 weeks. So at that point, you can stage your upgrades. But this scenario is when you deliver these components, I suppose, you define what systems get upgraded before other systems. So if we're upgrading 3 or 4 different systems on the locomotive because they're all being updated for track topology, a simplistic one for data, or we're upgrading an interface, getting some additional data from traction motor data, for example, because you want to use it in metadata analysis later, then we get a situation where this file, which is what we typically use, defines that, interaction. So what is upgraded first, but not only that, what can be upgraded in parallel? You don't necessarily need to upgrade one system, then another, and another. We're looking at efficiencies here. So we may have a dependency where we upgrade one, and then we can upgrade 2 or 3 others. And then we have a completion process, which then validates the updates, which again is run independently and typically last. So this file is defined and managed on the server side of the software update. It's also different based upon different loco configurations. So if you have 5 different types of locos, all with different vendor hardware, or even different versions of hardware running with different functionality, then we typically have different upgrade scripts that allow us to control and perform actions between each. So it could be cleanup actions, copying actions, the like. Everything you need to do as part of the upgrade process is defined on the server side, codified, and then sent to the destination, along with all your upgrades and data. This necessitates us following a very good process as well. Just because you're a software delivery and update tool doesn't mean you escape from the rigors of systems assurance. It's just as critical you go through a complete validation process. And this is another thing that operators are having difficulty with right now. They're going from a scenario where we have paid the vendor to do this work for us. So that's it, we're done. We look at a lot of the more complex software environments now, and I think ONSA released a advice sheet or whatever they call it recently, which again touched on some of these topics where you can't necessarily rely on a specific vendor to do what you need to do, particularly where there's interactions. You need to get directly involved. So in this particular case, test beds are going to become more and more required as we run. So as part of this process, it's necessary that we deploy software after we've deployed and validated against the test bed. For a lot of practical reasons, not just the fact that, okay, we've just wasted 3 days, but it's practical in that, for example, rollback. If you do an update, one of the things you want to achieve as part of your update is make sure you can roll back to the previous version. Now, while we like to think everything's perfect, a lot of you have probably dealt with software an awful lot. You know that occasionally it's not as perfect as what we'd like. And you only start seeing some of the issues when you start doing wider deployments and a greater level of use, because it's a time-based thing in some cases. So we do a situation where the software system has to also support rollback. Now, that's not always possible, particularly around some of the safety systems, but you have to work within your upgrade scenarios, and it's part of your planning in the process. So we'll move on to the next one. Accessibility. So this is where our comms comes in. So as we've said, the loco could be pretty well anywhere in the country. So if we get to a situation like that, we need to be able to have access to the loco. But as I said before, and we've come across this on numerous occasions, right when you're doing your critical update to your fleet of 300 locos or whatever it happens to be, you can't get to 5 of them because for some reason that particular area is out. So what we do to mitigate a lot of that is we pre-deliver. So part of the pre-delivery allows us to do a number of actions. So pre-delivery mitigates the volume of data. So again, in a lot of cases, we have low volume data systems, communication systems. So if we pre-deliver, it allows us to trickle the data over a period of time, and then it's available locally on the locomotive for an update at the time you require it. We perform post-delivery validation. Ultimately, these systems have to be extremely reliable. And we also have to, again, back to cybersecurity. we have to factor in things like, you know, CRCs and MAC validation if we want to get to security stages. Part of cybersecurity, again, is delivery of keys and things like that. You need to roll your keys regularly, so regular delivery. So you need to factor that in as part of the delivery process. So you're moving from just copying a file and relying upon your communications mechanism to make sure it's intact and complete, to a point where our dependency links or script, how you like to call it, then actually validates the data is intact. Because again, when we deliver data software and its accompanying data, because typically there's also a data update that goes with the software, it's got to be consistent across the different elements, not only across systems, but within the system as well. So we deliver a manifest. You've got to validate each of the files that are listed within the manifest are correct and haven't been tampered with, haven't been corrupted. And then we've also got, are you complete on the manifest? So have we got everything? So all of that's got to be built into the system that delivers the data. Now, there's other aspects as well. Now, quite often we trigger an update remotely, which doesn't require the copy, but it means some things may be offline. So that does present an issue, but it's less so on the newer systems. So when you've got centralized interlocking, your ATP typically requires your communications to its authorities. So ultimately what you have to do at that point is on startup, particularly for locos being in a workshop, for example, it validates on startup that it has the latest version of software before it'll complete its startup process. And most safety integral systems will do that anyway. All we're doing is overlaying this onto other systems to ensure you have integrity across your suite of software on the locomotive. So we do much the same thing. You start up, you validate, do I have everything correctly? It's not absolutely necessary, but you can also do that without comms. But it's then a business decision about whether you do that, because while you can upgrade to the version you had preloaded, it's not necessarily the latest version. So that's part of the upgrade sequencing and process. Physical access, that's particularly important. Again, while this is not necessarily possible, it's something that's advisable. Again, back to software, while we make it as reliable as we can, and the fact we've got multiple vendors, we can be in a situation where one of the upgrades didn't function correctly, so we have to roll back. Sometimes the rollback is either not possible or didn't function correctly, and you can't leave a loco in that state. So you have to physically attend the loco if you've broken it, basically. I think in the last 3 or 4 years, in the very first year, we only had a couple of locos out of thousands of upgrades that we needed to attend to personally. And since that point, we've not had to attend a loco since. Mainly because as we go through the failure modes, if they were missed during the initial design, they get updated. So we, again, try and improve over time to make sure that these issues that cause delays in the operation don't occur. So another factor. State. It's probably the simplest of the lot. It's essentially, we don't want to complete an update when a loco's, operating, when it's running on mainline, when it's shunting, all very bad times to try and do an update of your loco systems, because typically also, particularly down at the loco systems level, you want to reboot. You really don't want to reboot the braking computer while you're running. Not a good idea. So we have to at least consider and take note of what systems are updating, but also what we do when we update them, but then also when we update them. So some updates may require, or which are temporal, may require updating in sequence at a particular time, in which case then we have to organize with a rail operator to essentially shut down the system. And again, this becomes very similar to a safety systems update when you're upgrading your centralized interlocking. The difference with this is what we're trying to do is minimize the upgrade timeline from what could be days. If you've got locos distributed all over the countryside, you have to manually go and visit them to update them, and the updates required prior to you being able to operate the loco, then it could take a day or 2 days to actually get the system functional again, before the fleet, it comes on staged, but before the fleet is complete. Whereas what we're targeting here is to have it done in a few minutes, and validated at that point, and also have the list of the locos which we didn't get to. So if a loco's turned off in a workshop, do we know where the loco is? Okay, we continue to track that loco that's not been updated. So it's simpler, but it creates one of the biggest procedural and operational nightmares, is particularly when you have to shut a system down, Or if you don't have a temporal-based upgrade, we can do it on a geofence basis. So you get to a point where, okay, we won't upgrade a loco until it's basically at a loading point or parked in a siding at a specific location in the workshop. So that's where you get a situation where you support a scenario where we don't want to do an upgrade now. At no point should a software update override the loco systems if it's in run mode. Okay, so what do we need? The application itself. So we've talked a lot about this. So in order for a remote deployment to be successful, remote deployment must be well designed. So we've been through a lot of the aspects of what you need to build in, and it must be able to perform with the highest reliability. It may not be classified as a SIL4 system, but the level of business interruption you have is significant. And while I can't think of any scenarios just off my hat that may cause a safety incident, it is still a significant business interruption if it fails. So it has to be as the highest reliability you can make it. The server level configuration management needs to be performed. So we're going back into the systems management, which has typically not been performed an awful lot in data and systems to date. We're starting to get into that world where we're performing full-on configuration management at that level. We need a means to integrate and validate the process into the system. So again, we're interacting to a rail operator where we need to then try and overlay not just the systems and the software, but also the procedures to get the system working, which is often the hardest thing to do, is get people to change what they're currently doing. And we found the best approach to be is ease into the process. You stage how you do the updates, people get familiar with it, and you don't get into the full-on major system upgrade until you've had a chance for all the personnel to become familiar. A reliable transport mechanism that's both efficient and fast. So again, we don't want a situation where we're pushing data to a loco where if it fails for some reason or there's corrupt data, you send the whole lot again. It's not only bad practice from a software engineering perspective, it's not necessary. You can have, and there's plenty available if you don't want to build your own, and I recommend you wouldn't, plenty of things that do reliable and consistent and validated delivery. You still validate the complete set over the top, but the actual delivery itself means if there's a corrupted area in your file you're sending, which may be quite large, particularly if it's something like track topology, you can only send the bit that's not correct. So that works well. You need to include application and data validation. I've mentioned this a lot, particularly around the data validation, but you also have to validate that the application is not corrupt as well. You can't, the delivery application, you can't just ignore that, even though it's part of the delivery. You need to validate that as well. Sequencing, rollback, versioning, it's all standard stuff generally, but it needs to be adhered to throughout the process. Onboard integration modules. So again, you segregate your software into components, functional components. It allows you to perform an interface update without updating the rest of your software. So you try and abstract, particularly things that are tied to remote vendors, away from the core of the software. You don't build the whole set of software in one executable as an example. You have inter-process communications at that point. So you can abstract away your risk against update. So yes, you may be updating a remote system, but you try and minimize that impact on your software delivery mechanism. What else is there? So I suppose high-level remote software can be considered configuration management exercise. That's really what it is. While that's true, it's much more complex because you've got so many different more moving parts and so many more things you should be doing. Now, you can copy a file down and execute a script easily, but all the things you should be doing to make it reliable and effective, that's where it becomes a lot more complex. I suppose I'll look at some a little bit more. We've only got a few slides left. Are there any questions at this point, given I've just gone through a fairly major chunk of functional components?
We have, David. We've had quite a few questions come through, as you could well imagine. So I'll try and get through a couple of them, as many as I can anyway, and then allow you to wrap up. One question here: in order to make software delivery more efficient, how far has the industry adopted more automated whole of system testing and the management of configuration data?
So again, across all the systems we deal with, there's very few that implement a system level functional test. It's getting more prevalent now, and a lot of those organisations that have a little more cash, so or are required by legislation, fear of the public, they have a tendency to apply a little bit more. But typically, I found that the systems that are currently running in distributed interlocking environments, typical isolated environments, are still running that way. As Matt said in the beginning, we still haven't made the major transition to a fully integrated system solution. What you find is, because of those aspects that push you into integrating your applications, they also push you into integrating your test beds and your delivery tests. And my view on this subject, and this becomes fairly significant, is you need to automate these tests and deployments. Now, you can't necessarily automate everything, but you can automate most of it, because what it does, while it imposes an upfront cost on your delivery, it saves you money from that point on. Because instead, like, let's take an example of an update. It may take 2 months to 3 months to fully validate across a fleet of multiple different locos and the like. If you can automate that process, it may take you a year to build your automation suite, but at that point, every time you deploy, your full suite of tests may only take 2 weeks. So it's not that it reduces it to nothing. It's a really good idea, but I think the industry hasn't got to the point of maturity where it's adopting it completely yet, but it is moving in that direction. And it's being pushed in that by the newer, sort of centralized based interlocking systems, so ETCS style arrangements.
Great. I have another question here. What are the differences between high integrity software systems and systems with lower integrity requirements?
That's part of how you can deal with your upgrade process. So you have to deal with the high integrity systems a bit differently. You can't break the validation process, your assurance process. So as an example, when you do your validation on a Silver ATP, you've got to validate the complete suite. You put hardware, your software, your libraries, everything's integrated to that subsystem. So what you have to do is ensure in that particular case the delivery matches that process. Then, again, because of your assurance requirements, you can't have just reading version numbers off that, for example, and validation of file checksums. You've got to have an independent process that then checks that and feeds it back independently. So you have your 2 layers of validation. So that's probably the main one. Where you have your non-critical systems, could be your video surveillance system, for example, you don't have the same requirement. So you don't, while we do check, for example, your versions to make sure the system's up to date and you're validated against the manifest, you don't have the same restrictions on being able to update the system. You can update components to make it more efficient.
Great, thank you very much. I have one more question. There's a couple more here, but there's one, and it's probably actually more for me to answer in this case than yourself, but I'd be interested to hear your thoughts as well. Condition monitoring is a growing area for trackside equipment. To maximise profit, vendors are naturally trying to vertically lock in their customers with incompatible systems, which are more costly to integrate and maintain and more risky long-term to support. What progress is being made to deliver standards for interoperability that can steer the industry towards the best interest of the rail infrastructure maintainers? Now, I can answer part of that. So currently there is the National Rail Action Plan, which is being supported by federal and state governments, and also RISSB and a number of industry bodies, where we're looking at a lot of different things, and which is mainly centered around harmonisation and interoperability. On top of that, RISSB is currently reviewing the AS 7450 Rail Systems Interoperability Standard with the intention of, I suppose, in reinforcing a number of the requirements within that standard with the aim to drive industry towards more interoperability. So that's what's happening at a national level. Did you have anything that you wanted to add to that, David?
I did take some bits out of some of the slides a bit earlier on that basically says, as part of the process, we should be pushing as people involved in the rail industry to have a level of interoperability. And while everyone thinks of interoperability from a specific system-to-system perspective, they don't consider how you get the systems updated or delivered and managed. So definitely that's a required process, but just don't forget the actual how we get the systems there, and cybersecurity as well. We can't leave cybersecurity out of it because, again, it means we can't put you know, passwords root on our box on the loco and expect that to be there forever.
Yeah, cybersecurity is certainly a major consideration when we talk about interoperability. I'm mindful of the time, David, so I'll throw back to you to finish off your presentation.
Okay. So that's not much to go. So we've been asked, you know, what would it take to use what we've built for some customers elsewhere? And it's not an easy question because the systems that are built very much tailored to the systems that are deployed in that particular rail environment. So, you know, Wayside uses their particular systems, Onboard locos use their systems, and you can have choices ranging from different loco manufacturers, different braking manufacturers, the whole lot. So it's very customized to the specific environment. What we do as part of this delivery is we use what we call a toolbox. So that's the best way I can describe it. We have mechanisms for building a configuration data set. We have tools for delivery of files. We have tools for validation of file-based interfaces. We have a data abstraction layer that allows us to use files, databases, spreadsheets, whatever it happens to be. So the way we do it, and the way I would recommend anyone does it, because it's such a diverse system, is you build a tool set that you construct your final system out of. And that's the best way you get to remote deployment. And this is, I've got a comment here. What I say? Standardized application management model is unlikely to be adopted by the rail equipment manufacturers. So if we can get these standards out and have them adopted, it would be magic. It would make our life so much easier. But I don't see that happening in the very near future. It's going to be a fairly long path, particularly as a lot of the equipment is manufactured overseas and we have a lot less leverage than we would otherwise have. But yeah, standardization would help significantly. But until that point, you need to rely upon both the vendors' willingness to participate to make things easier, and if all push comes to shove, you then need to also obviously get involved at the data layer and actually have a look at what they're doing. Summary of benefits, I suppose, again, mindful of the time, we're hours up. There's two key benefits, I suppose, if you look at this holistically. It really boils down to time and safety. So safety is probably the simpler one. The typical traditional railway system doesn't have centralized signaling. It's all distributed signaling. And with distributed signaling, you don't have the same sort of constraints as what you would have in a system, your ETCS, CBTC, ATMS type systems, where you've got a lot of components that, you know, your components on board are half of another system that's sitting in a server at the back office. So there's so much more tighter coupling at that level. And it relies upon communications and everything integrally. It also relies upon data to a much greater degree for things like track topology. So we've been through most of that. So that's where your safety comes in, where not only you increase the reliability of the system being delivered, but you can ensure that the systems that have been delivered are what you would expect and what you expect to be there. And you know when they haven't been delivered as well. So that's another thing. We have seen a lot of scenarios where we have ATPs being upgraded and neither the person doing the update or the checker running behind has picked up errors, such as, for example, wheel diameter. where some of the ATPs require you to manually configure wheel diameter. And that does impact, obviously, your distance to target and things like that. So it's pretty important in that respect. Time very much impacts time. These systems are so much more complex and interconnected that the time to deploy, just the time and the logistics to work out what you have to deploy takes time. So overlaying this over the top takes your interruption down from hours or days down to minutes if you can manage it. Now, it's not always the case. Some updates may take you an hour if you could do a complete systems update everywhere, but it does reduce the time quite significantly. There are some secondary factors, I suppose, around, I suppose, remote fleet management. So you can determine positions and things like that. I suppose, what else is there? Overall savings in time directly correlates to rolling stock runtime. So if you've got your rolling stock more utilized because you haven't taken it out of service, it's not so critical at the moment in passenger rail, but more freight where you don't want your rolling stock sitting still. Because at least in passenger, you've got usually some time at some point during the night to update your systems. But even then, you want to update them in a timely fashion. You want to know that they're updated successfully and not have to have people running around manually doing updates. And that's it. I think we've run out of time, gone slightly over time. So I don't know whether we have time for a couple more questions.
No, I thought, unfortunately, we're going to have to call it at that, David. So, look, thank you very much for your time. And Matt, I really appreciate everything you've presented today. It's been really, really interesting. I'm sure that many people have got a lot out of it. And to everybody else, thank you so much for joining us for our last webinar of the year. We really look forward to presenting you another really interesting program next year. All the best for the holiday season, and we'll see you in January in 2021. Goodbye.
Goodbye.